Okay. Today we'll start the new chapter, which is the chapter 7. Already we have completed the chapter 3, 4, 5, 6. Okay, up to chapter 6 we have completed. Now we have to look at the chapter 7, 8, 9, 10. 4 more chapters left. Okay, so that means 4 class. We need 4 more class, 4 to 5 class. This week we will have 2 more class. I'll take an extra class this week, inshallah. Today is Sunday. What is the status of tomorrow? Is it possible to take a class tomorrow? Ismail? Ismail, you are there? Mithun, Diba, বাকিরা কই? ইয়েরে বলো, মনিরকে বলো।
অলরেডি মনে দেখছে খেলা দেখছে তো সকালে আজকে সবাই।
সকালে খেলা ঠিক আছে। কোন দল ছিল?
আমি তো আছি
ব্রাজিল।
ভালো লাগে না স্যার।
দিবা কোন দল ছিল?
স্যার আমি আর্জেন্টিনা।
হ্যাঁ, কোন দল ছিল?
স্যার আমি আর্জেন্টিনা ছিলাম।
আচ্ছা, আর মনির?
মনিরও মনে হয় আর্জেন্টিনা।
এই জন্য কি মিছিলে চলে গেছে?
বিরিয়ানি বাগাই করে রাখি।
আচ্ছা, আমরা শুরু করে দিই, নাহলে লেট হবে, যেহেতু আজকে তোমাদের অন্য ক্লাসও আছে।
আচ্ছা স্যার।
Okay, so today we'll start the steady state error, which is chapter 7. So first of all, let us look at the contents we are going to discuss today. Sources of steady state error. So we have to find out what are the sources of the error and what would happen if we have the unity feedback system, and what are the static error constants and system type, and steady state error for non-unity feedback systems and sensitivity. Okay, among these, I think I'll show you another thing, which is the industrial control system. Okay, I'll show this slide also today, inshallah. So first thing first, let us introduce the steady state error. So what is the steady state error? The definition is given here. Steady state error is the difference between the input and the output for a prescribed test input as t tends to infinity. So it is a difference between what? Between the input and the output for a prescribed test input as t tends to infinity. So it is a difference between the input and the output for a prescribed test input as t tends to infinity. That is the steady state error. Okay. So see, so if you give the input and if you get an output for an input, then the difference between the input and output is called the steady state error. Okay, if you do remember that something like, say, a feedback control system, that is plus and that is minus. The difference between this is the error. That is input, that is output, and this one feedback. Okay. So difference between the input and the feedback is the error. That is the steady state error. So what I have written here, I have write a closed loop control system. Here the difference between the input and the feedback is called the steady state error. Okay. Difference between the input and output for a test input as t tends to infinity. Okay. And we are concerned with the difference between the input and output of a feedback control system after the steady state has been reached. Our discussion is limited to a stable system. We are concerned about the stable system, but the natural response approaches zero as t tends to infinity. So natural response tends to zero as t tends to infinity. That means the difference would become zero. Okay. Whenever the difference would be zero, then the system would be stable. Okay. So what is the stable system? We know from the previous chapter that the response curve of a stable system. Do you remember what is the response curve of a stable system? It is something like that. That is a stable system. Okay. So we are concerned with the difference between the input and output of feedback control system after the steady state has been reached. Our discussion is limited to stable systems, but the natural response approaches zero as t tends to infinity. Okay, let's move on. What are the sources of steady state error? Sources of steady state error. Some names are given here. Many steady state errors in control systems arise from nonlinear sources, such as backlash in gears or a motor that will not move unless the input voltage exceeds a threshold. Nonlinear behavior as a source of steady state errors, although a viable topic for study, is beyond the scope of a text or linear control system. The steady state errors to study here are errors that arise from the configuration of the system itself and the type of applied input. Okay, see, so many steady state errors in control systems arise from nonlinear sources, such as backlash in gears or a motor that will not move unless the input voltage exceeds a threshold. Nonlinear behavior as a source of steady state errors, although a viable topic. Okay, so what is the source of steady state error? It arises from the nonlinear sources, such as backlash in gears or a motor that will not move unless the input voltage exceeds a threshold. Okay. So nonlinear behavior as a source of steady state errors, although a viable topic for study, is beyond the scope of a text on linear control systems. Okay. And steady state errors for unity feedback system. Say, if we have the unity feedback system, then what would happen? Steady state error can be calculated from a system's closed loop transfer function Ts or the open loop transfer function Gs for unity feedback systems. So see, what is the closed loop transfer function? Closed loop transfer function is represented as Ts, and open loop transfer function is represented as Gs. Okay. Let's see. Steady state error in terms of TS. Okay, they have considered a figure. Consider this figure. This is a closed loop system, definitely. It is a general representation. It is a representation for unity feedback system. Yes, RS minus CS, right? ES into RS minus CS, and here is into RS minus same. RS minus CS, but CS is equal to what? RS into TS. We know that CS is equal to RS into TS. Now put this value 7.3 into the 7.2. Then we'll get what? S is equal to RS into 1 minus TS. TS is equal to RS into 1 minus TS. How it comes? Look at here. ES is equal to ES is equal to RS minus RS into TS. RS into TS. And if we take it common, RS 1 minus TS. Okay. So we get this one. RS is ES is equal to RS into 1 minus TS. 7.4. Now, although equation 7.4 allows us to solve for ET at any time t, we are interested in the final value of the error. That means E infinity. So we are considering the final value of the error, which is the E infinity. Applying the final value theorem, which allows us to use the final value of ET. We're taking the inverse Laplace transform of ES, then letting t approach infinity, we obtain. So we can write like this: t tends to infinity, limit ET, limit S. ET means what? S into ES. ET S into ES. So instead of ES, we'll write this one. Okay. So that is the equation. Now take a look at the problem, 7.1. Find the steady state error for the system of figure 7.3a if TS is equal to, and the input is a unit step. So see, input is a unit step. That means RS is equal to 1 over S, and TS is given. So from the equation 7.4, what I'll get? TS is equal to RS into 1 minus TS. So RS is given, TS is given. So how it comes? Yes, is equal to RS. First of all, put the value of RS. That means 1 by S. The first bracket, 1 minus TS. TS means 5 S square plus 7S plus 10. So right, s square. I don't know. My mouse has some problem, I think. 7s plus 10. Here, s square plus 7s plus 5. Mm, 7s plus 5. Okay, so something like that. Now, so then is it stable or not? So find the stability, you need to bring the table, root table. So for the root table, what we have to calculate? We have to calculate the both j omega axis. See s cube plus 7s square plus 7s square plus 10s. So if I take that root table, so what I have to write? S cube s square is to the power 1 0, and s cube, this is 1 and 10 s square 7 s square 7 0 s to the power 1 70 minus 10 minus 10 here, it would be 0, and s to the power 0, the value would be 7 minus 10 0 0. Okay, does not have a right half plane pulse or geometry pulse other than that at the origin. Okay, something like that. Okay, so you have to check like this. You can, so if you apply this value, then so let me check this one 1 7 1 7 and 0 and 0 divided by 7. If you calculate it, 0 minus 70 by 7, that means it's a 10. If you put the minus, then it will be okay. Okay. So like that. So no change. See, no change. So does not have a right half plane poles. Geometric poles on the other than that the origin. So we can apply the final value theorem. Since there is no change in the first column, so it is a stable system. So we can apply the final value theorem. So equation 7.7, put this one into equation 7.7. Equation 7.7, which one is the equation 7.7? Substitute equation into equation 7.5. 7.7, put this one into equation 7.5. Limit s tends to es. S tends to es. So now put the value s as the 0. Then you get the value half. How it becomes half? Let me calculate. Infinity limit tends to 0 s into es. Es means this value. Then s should be s square plus 7s plus 5. Then s into square 7s plus 10. Then s should be cancelled out. If you put the value 0 here, then 10 is there and 5 by 10. If you put the s equal to 0, then 5 by 10. Then you'll get half. See, e tends to infinity, become half. Okay, this is the steady state error in terms of GS. Now look at the steady state error in terms of GS. GS is the open loop system. As you know, we know that what is the open loop system, RS minus CS difference and CS equal to S into GS. But put this value CS here, RS minus so now finally we get what? We get the value is equal to RS divided by 1 plus GS. Okay. 1 plus GS. Now put this value in the final value theorem. Then we will get this one. Limit s tends to 0, SRS divided by 1 plus GS. Now, if you have the step unit, that means 1 by s, then the equation would be look like this. And if you have the ramp input, then equation would be look like this. And this one for the ramp input. If you have the parabolic input, then for the parabolic input, the equation will be like this. So say, step input, that means Rs is equal to 1 over S, ramp input 1 over S square, and parabolic input 1 over S cube. So these are the three things: step, ramp, and parabolic. Step, ramp, and parabolic input. Okay. Step, ramp, and parabolic input. Now see the step input 1 over 1 plus limit S tends to 0 GS, and ramp input 1 over limit S tends to 0 S into GS, and parabolic input 1 over limit S tends to 0 S squared GS. Okay, so for the three kind of inputs, we have three equation. Now see, suggested errors for systems with no integrations. Let's see, there is the equation. This one, find the steady state error. Steady state error for input 5 UT, 5T UT, 5T square UT to the system shown in figure 7.5. So this is a feedback control system for example 7.2. So now see a step limit this one 5 divided by see 5 UT. That's why this comes 5 UT 1 plus limit s tends to 0 GS. So GS is equal to what? Here put the value s equal to 0. If here s equal to 0, then 3 into 4, 12. And here the 12 and s0 plus 2, that means 120 into 2. So this is 10. That means the 20. Here 20, so 5 by 20. And similarly, if you have the 5T UT, that means 5 by limit extends to s into GS. So GS s equal to 0, that means the 0. Lower part is 0, so it would be infinity. And for the 5T square UT, 10, that means 2. 5T square, limit s square GS. Okay, 7.20. 2 times. For the input, whose Laplace transform is 10 by s cube. This error will be 10 times as large as that given equation. So if you take the Laplace transform of this one, then you will get the 10 by s cube. So put the value, you get the infinity. So see, on the step input, you have the value. Otherwise, you do not have the value. Those are infinity. Okay, static error constants and system type. In the previous section, we derived the following decision for steady state error. For a step input, ut is equal to say step input this equation, ramp input this equation, and parabolic input half t square ut this equation. Now these portions. Let's say for the step input it is kp, and for the position constant, that is kp, where limit extends to 0 GS. Velocity constant, which is the kv, where kv is equal to limit extends to 0 s into GS, and acceleration constant k, limit extends to 0 s square GS. See, three static error constants. These constants are known as static error constants. Okay, remember, we are considering these constants as the static error constants. Static error constants. Kp, kv, k. Now equation. No problem is there. Three equations are there. each of them find out the static error constant. See the static error constants. First one, Kp limit distance to 0 gs, Kv limit distance to 0 sgs, K limit distance to 0 s square gs. So Kp, find the value Kvk. So for the step input, for a ramp input, for a parabolic input. And that is the first one. Okay, very simple, not that difficult. Okay. Kp limit distance to 0 gs 500, just put the value Kv limit distance to 0 sts 0 K limit distance s square gs 0. Okay, similarly, similar thing. First of all, find out the Kp, Kv, Ka, and then put those value. Say for the second one, you will get a value for the ramp input. Now look at the figure. Look at the figure. Okay. For the third one, Kp, Kv, Ka, the K has a value. So if the K has a value, then the parabolic input has a final output. Error will be there in the parabolic input. Other cases there are no error. Okay, it is not difficult, it is a simple one. Just take a look at this and solve it. It's a feedback control system for defining system type. So see, a table you have to consider. You have to remember a table. A step, ramp, and parabola. Three kind of input are there. A step, ramp, and parabola. A step 1 by 1 over 1 plus Kp. Steady state error formula. And three kind of error are there: type 0, type 1, and type 2. In the type 0, Kp is a constant, Kv and K would be 0. And the error would be for the Kp 1 by 1 plus Kp, and for the Kv and K would be infinity. Type 1 error, Kp infinity, Kv constant, Ka 0. That is the type 1. For this, error is 0 for Kp infinity. Kv is constant, and the error would be 1 over Kv. Ka is 0. As a result, it would be infinity. Error would be infinity. Similarly, type 2, Kp and Kv both are infinity. K is constant, and the error would be 1 over Ka. Okay. These are the relationships between the input system type, static error constant, and steady state errors. Okay, input system type, static error constant, steady state errors. 1, 2, 3, 4, 4 things. Okay, remember this table. Now see, steady state error for non-unity feedback system. So if you have the non-unity feedback, then what would be the steady state error? This kind of figure is there. Okay. Non-unity feedback control system, for example, 7.8. So this is the figure for which we are considering the steady state error for non-unity feedback system. So this feedback system, how, let's look at the procedure. What is the procedure? First of all, take a look at the questions, what they have said. For the system shown in figure 7.16, find the system type, the appropriate error constant associated with the system type, and the steady state error for unit step input, assume input and output units are the same. Okay, all are the same unit. So first of all, let's see, that is GS and that is HS. And what will be the total value? GS divided by 1 plus GS into HS minus GS. That comes from the formula. Now put the value, do the calculation, then you will get this one 1 into 100 into s plus 5 divided by s cube plus 15s square minus 50s minus 40. Okay, so now you have to find out the value Kp, Kv, Ka, all three. They have find one. Kp has a value minus 5 by 4. Then the error would be 1 by 1 plus Kp. Just put the value of Kp, you'll get minus 4. The negative value of a state here implies that the output step is larger than the input step. That means the output is larger than the input. In that case, negative value would come. Okay. Another one, sensitivity. What is the sensitivity? Okay. During the design process, the engineer may want to consider the extent to which changes in system parameters affect the behavior of the system. Ideally, parameter changes due to heat or cold, heat or other causes should not appreciably affect the system's performance. The degree to which changes in system parameters affect system transfer functions, those parameters is called the sensitivity. Sensitivity is actually a degree at which the system can change, maximum change. The system with zero sensitivity is ideal. The greater the sensitivity, the less desirable the effect of a parameter changes. For example, assume the function f is equal to k by k plus a. If k is equal to 10 and a is equal to 100, then f equal to what? F equal to would be 0.091. If parameters triples to 300, then f equal to 0.032. We see that a fractional change in parameters a of 300 to 100 by 100 to 200% change. It's a change in the function f equal to 0.032 minus 0.091. Okay, so minus 65% change. The function f has reduced sensitivity to change in this parameter a. As we proceed, we will see that another advantage on feedback is that in general it affords reduced sensitivity to parameter changes. So sensitivity formula is this one, P and F divided by F and F. Okay. A problem is given for the sensitivity, find the, so given the system of figure 7.19, calculate the sensitivity of the closed loop transfer function to changes in the parameter A. How do you reduce the sensitivity? So closed loop transfer function, so find out the closed loop transfer function and the sensitivity A by T, delta T by delta A. So A by T, we have found the A. Now you have got the T value, put this value, do the calculation, then minus AS by S square plus S plus K. Okay, that is chapter. Okay, so this is all for the chapter 7. That's all for the chapter 7. So chapter 7 has been finished. Do you have any question regarding this? I don't think so. Let me take the attendance. 1, 14,
Yes, sir. Yes, sir.
6, 3, 10. 1, 14, 6, 3, 10, right?
Yes, sir. Sir, please send your
Yes, sir.
video and lecture.
I already today I have uploaded
Video
the
upload.
yeah, I uploaded the lecture sheet already. You check the classroom as well as inshallah I'll upload the video.